40,000 kilometers of new roads appear across the United States annually. Nearly 30% utilize concrete designed to last 40 to 50 years. These routes carry loads of several dozen tons without deformation. But this is just the beginning. Why compare road beds to skyscraper foundations? At first glance, laying a road seems simple, but in reality, the soil is compacted firmly to support the immense weight. Steel reinforcements are positioned with centimeter-level precision. One can notice how massive paving machines, stretching dozens of meters long, operate like industrial robots directly on the site. This engineering turns a pile of raw materials into the most durable concrete roads on Earth. The surface settles calmly. 30% of the federal highway system in the United States relies on cement concrete. One can notice the distinct gray hue of these roads, contrasting with common asphalt. While the surface may not offer the same smooth driving feel, technical advantages prioritize it for major highways. But this is just the beginning. Why is this material preferred for major arteries? Comfort seems key, but longevity dictates the choice. Concrete lifespans reach up to 34 years, exactly twice that of asphalt roads. It seems obvious that heat affects all roads, but in reality, concrete resists warping and sinking under heavy truck traffic. Continuous paving machines lay 3 to 5 kilometers in a single day. It is visible how this technology significantly reduces project timelines. The equipment gradually completes the solid path. The route is ready for decades of heavy use. Two specific parameters, the strength and quality of the soil, are analyzed to ensure the schedule holds, significantly reducing project timelines. The first step in building a concrete road involves checking the root and ground conditions. Engineers look at the terrain to understand the rock and soil underneath, calculating exactly how much dirt needs to be removed or added. They also consider how the work might affect traffic and the environment. This data helps them decide the best way to build the road, determining how many lanes it should have or how long the route will be. But this is just the beginning. The construction team gets to work immediately once the plan is approved. One can notice how the machinery clears the area and removes plants to prepare the site. The roadbed is raised or lowered to match the land, while the soil foundation is compacted to support the concrete pavement and future vehicles. A grader levels the top layer of soil with mechanical precision. Why are underground systems like electricity, water, and drainage installed at this exact moment? The ground seems ready for the base, yet the process pauses. Installing them now ensures the foundation remains undisturbed during later stages. Therefore, roads without sidewalks may also have drainage ditches built along both sides. Everything only gets more complicated. The contractor begins building the road base, the middle layer, once all underground utilities are finished. At first glance, spreading crushed stone seems like a simple task, but in reality, it is critical for transferring the weight from the concrete surface down to the soil. A layer of large crushed stone is spread evenly across the ground. A vibratory roller or steel wheel roller compacts it to make sure it is firm and uniform. Depending on the terrain and expected truck traffic, this layer is built in multiple levels. It gets more complex further on. It is visible how a thicker bottom layer supports a finer top layer to create a stable surface. Heavy rollers continuously move back and forth across the entire roadbed. This compacts the soil and stone to increase load-bearing strength and reduce the risk of future settling or cracking. Because moisture determines density, a water truck drives ahead of the roller. It helps soil particles bind together by keeping the ground at the ideal moisture level. This compaction stage can normally take anywhere from 2 to 4 days depending on the length of the road. And this is not the limit. Field technicians closely monitor the entire process using compaction gauges and vibration sensors. Laser surveying equipment ensures all measurements stay within allowed tolerances. and the crew moves on to the most important stage, pouring the concrete surface. 4 or more distinct types of heavy aggregates are stored in separate compartments to ensure the perfect recipe for industrial concrete. Wheel loaders or conveyor belts tirelessly load raw materials like crushed stone, fine sand, or gravel into these inline storage silos. Depending on the customer's specific setup, the huge compartments are constructed from reinforced concrete or steel. All of this material is supplied by an industrial batching plant where ingredients are mixed with near-perfect accuracy. But this is just the beginning. Why is every gram of aggregate weighed on a calibratable belt scale system? At first glance, rough estimation might seem sufficient for construction, but in reality, any deviation ruins the chemical balance of the batch. The equipment measures the exact amount needed based on preset mix designs to guarantee structural integrity. One can notice how the weighed aggregates drop into a large capacity feeder bucket, which ensures that every stone is fully discharged without leaving any leftover residue. The dry base is transported to the next station for the liquid phase. Water enters the process from local supply networks or dedicated on-site storage tanks. It is fed into an independent weighing system and released into the mixer via free fall or through high-pressure spray nozzles, depending on the plant configuration. In parallel, dedicated dosing systems inject chemical admixtures such as super plasticizers or accelerators. This separation ensures accuracy and prevents any risk of cross-contamination between active ingredients. It gets more complex further on. A high-performance concrete mixer, either a pan or twin-shaft variant, takes over the operation. It is visible how the internal mechanisms blend the components into a high-quality mixture within a remarkably short cycle time. The finished concrete is discharged directly into the rotating drums of ready-mix trucks, waiting below the structure. The transfer happens immediately to maintain the continuous flow of production. Drivers must move with calculated urgency because the concrete remains viable for only 1 to 2 hours on average. During the journey, the mixing drum rotates ceaselessly to prevent the heavy material from separating or setting too early. Once on site, the truck carefully approaches the concrete paving machine to offload the system. Thus, the fresh surface material is ready for immediate application. $120,000 is the starting price for a machine that turns raw mix into a highway with mathematical precision. When the truck arrives, the concrete is discharged directly into the receiving hopper of the concrete paver using a chute or a powered conveyor. This specific phase of operation demands absolute and tight coordination between the truck driver and the paver operator. Why is such strict synchronization necessary during the discharge? It might seem that a short pause in supply is harmless to the final result. But to ensure that concrete is supplied evenly and continuously, preventing gaps or delays in the paving process, a line of mixer trucks is scheduled in rotation. For long-distance paving or highway work, there is always one unloading, one arriving, and others queued up waiting their turn. In modern setups, the conveyor connects directly between the truck and the paver. This helps speed up the feeding process and reduce material loss during transfer. As soon as the concrete is fed in, the slip-form paver automatically spreads it evenly across the prepared subgrade. One can notice how the machine follows the exact width, thickness, and elevation specified in the design. There is no need for any follow-up rolling or manual leveling, but this is just the beginning. Deep within the machine, a powerful auger or spreader continuously moves the heavy mix forward. It distributes the material uniformly before it enters the forming mold. Built-in laser sensors, GPS systems, or 3D guidance tech ensure that the final surface stays flat, level, and aligned. At first glance, the machine seems to merely smooth the top layer, but in reality, it is fully equipped with vibrating pans and a slip-form mold that compact and shape the concrete while it is still wet. During paving, the machine automatically feeds round steel dowel bars from its internal storage tray. It places them in the middle of the fresh concrete. These bars are set across the width of the road, right at mid-depth. They help transfer the load between adjacent concrete slabs and reduce cracking at the joints. Thanks to the built-in dowel insertion system, this step is done fully automatically without stopping the machine or interrupting the paving process. It creates a seamless monolithic slab that is stronger and more durable. Even on long winding road sections, the mechanical work does not stop. Machines like these typically cost anywhere from $120,000 to over $300,000, depending on their size, configuration, and level of automation. With high output and extreme precision, slip-form pavers are now the gold standard for building large-scale concrete roads worldwide. Immediately after finishing, a liquid curing compound is sprayed over the entire concrete surface. This coating helps retain moisture, preventing rapid drying. Everything only gets more complicated as the material sets. A few hours later, once the concrete begins to harden, workers use special saws to create expansion joints at regular intervals. It is visible how the blades cut through the hardening surface, leaving precise lines. These joints allow the concrete to expand and contract with temperature changes without cracking, preserving the surface over time. A few hours after the joints are cut, workers clean out all the dust and debris inside the gaps. Then they pump in a layer of special sealant, usually polyurethane, silicone, or bitumen. This viscous sealant keeps water, dirt, and other materials from getting into the joints. Without it, water could seep down through the cracks and cause peeling, cracking, or even damage the base layer underneath. After the entire concrete pouring and initial curing process is complete, workers begin by marking the traffic lanes with yellow paint. And this is not the limit. They place no entry signs to block vehicle access for at least 7 days. This allows the concrete to fully harden and reach its design strength. During this period, the roadway is strictly off limits to any traffic or heavy loads that could damage the surface. Finally, site engineers conduct a full inspection and final quality check, including compressive strength tests, surface flatness assessments, and uniformity evaluations. Thus, the road is officially prepared for heavy use. Dozens of workers must coordinate in real time to match the output of a single machine, common in the United States. All this manual effort takes place before strict conformity evaluations officially open the road to use. While slip-form pavers automate the process elsewhere, road construction in developing nations like Peru often relies heavily on manual labor. Why choose such an exhausting method over high-tech automation? Heavy machinery seems like the obvious choice for speed and consistency. However, accessibility and budget constraints in remote areas dictate that human hands must take the lead. One can observe the concrete pouring directly from mixer trucks down angled metal chutes onto the prepared ground. At first glance, spreading the heavy mixture with shovels and rakes seems simple, but in reality, the concrete begins to set almost immediately, demanding urgent speed. Any delay can cause the material to harden before it is properly leveled. Crews utilize long screed boards to manually distribute the mass across the width of the lane. But this is just the beginning. Operators insert handheld vibrators into the wet slab to compact the material and force out trapped air pockets. It is visible how the surface becomes denser and more uniform under the influence of the vibration. Following this step, finishers use steel floats and hand rollers to trowel and texture the road. Without guided systems, the team relies entirely on experience to judge flatness. The process is only gaining momentum. due to the lack of automated leveling sensors, achieving high precision in elevation becomes difficult over long distances. This labor-intensive method remains common where modern technology cannot easily reach, highlighting the contrast in global infrastructure development. The manual paving concludes as the concrete begins its curing process. 4 years of grueling labor were required to complete a 4-lane highway cutting across the Taklamakan Desert, known as the Sea of Death. Hundreds of bulldozers were deployed simultaneously to flatten the dunes in one of the most advanced infrastructure projects in Asia. They cut down high ridges and redistributed the sand into lower areas to create a smooth, balanced surface. The goal was to build a foundation strong enough to support heavy construction machinery without the risk of sudden collapse. But this is just the beginning of the struggle against the shifting terrain. Why is such strict supervision required during the leveling process? To the naked eye, the desert floor might look uniform after the machines pass. However, surveyors meticulously check elevation and slope to ensure uniformity across miles of open desert, preventing future structural failure. One can notice how conveyor systems push excess sand away from the work zone, while compactors gently press the top layer. Yet, mechanical flattening is not enough. Engineers discovered that injecting water into the loose surface helps bind the grains together. Using long sprinkler arms and underground pipes, they spray controlled amounts of groundwater across the site. Moisture penetrates several inches deep, creating a denser and more cohesive layer. It gets more complex further on. Heavy rollers move in immediately after the sand reaches the right level of dampness. It is visible how they compact the surface to remove air pockets and lock the particles in place. The constant rumble of steel drums echoes across the desert as each pass turns soft, shifting sand into a firm, uniform base. By the time the surface dries under the desert sun, it has hardened enough to carry the weight of cranes, mixers, and supply trucks. At first glance, a solid foundation built from nothing but sand and water seems unstable, but in reality, it is the only way to proceed before adding reinforcement. Workers begin spreading a base layer of soil over the stabilized sand. Dump trucks pour out loads of reddish earth, which bulldozers then push and level across the area. This layer adds weight to the sand below, strengthening the surface and keeping it from shifting under heat or vibration. Transition to the next level. Portable asphalt plants roar to life at the edge of the desert, heating stone, sand, and polymer-modified bitumen to nearly 170 degrees Celsius. Insulated tankers deliver this hot mix non-stop to the paving machines waiting on site. One can notice the glowing asphalt being spread in layers about 6 centimeters thick. Steel rollers follow close behind, compacting the material before it can cool. This process repeats in a tight choreography, with the paver, roller, and finisher moving forward like a synchronized machine. The first passes use heavy steel drums for compression. The final ones switch to rubber tire rollers, which knead the surface to seal tiny air gaps and create a smoother texture. And this is not the limit. Thermal sensors on each paver track the surface temperature in real time. If the asphalt drops below 140 degrees Celsius, rolling stops immediately, otherwise cracks could form once it cools. Supervisors check flatness with laser beams, allowing no more than 3 millimeters of deviation per meter. As the desert wind cools the surface, the asphalt hardens into a flawless black sheet. It becomes tough enough to withstand temperature swings from -25 to +70 degrees Celsius. To finish, workers spray a protective seal coat, giving the surface its signature deep shine and locking out moisture. By dusk, the newly paved highway gleams under the sinking sun like a dark, mirror-like ribbon stretching across the golden sea of sand. What had once been an empty wasteland now reflects the light of progress, born from heat, steel, and human endurance. This project connects the far ends of Xinjiang, showcasing an engineering achievement that impresses experts worldwide. Zero deviations in the surface profile meant that even American engineers couldn't help but be impressed by the structural result. This operation concludes the technical breakdown of how concrete roads are built, comparing methodologies from the United States to China. All engineering information was carefully gathered from various reliable sources to ensure compliance with standards. But this is just the beginning of the road's life cycle. One can notice how the cured concrete forms a seamless, durable layer across the landscape. The surface reflects the sheer scale of the construction effort. Why is such strict attention paid to the accuracy of the data? At first glance, the paving process seems complete and self-sufficient. But in reality, verified records are necessary to guarantee the road's longevity under heavy traffic. If specialists spot anything inaccurate in the final report, the segment undergoes immediate revision, preparing the facility for the next stage of operation,